Hello, and welcome to our overview of metals and where we're going in talking about metals. This will be chapters 2 and 3 in your textbook. So when we think of metals and we think of civil engineering, most likely we're thinking of steel. But you could be working with aluminum, who knows, maybe a fancy titanium alloy. It's hard to say what's coming in your future. As we look at this photo of the steel construction for the Sobrato campus, I know that those wide flange columns and beams are made from grade A992 steel that has a yield stress of 50,000 psi. But when I was a student, A992 grade steel was not the common steel, didn't exist, and we had to use A36 steel, which only had a yield stress of 36 ksi. So the information that's coming in this video is that information that material scientists and engineers needed to create these new steels for us to use. It's really kind of cool. And the metal that we've been using to construct buildings has been evolving over time. We started with cast iron, but cast iron has a very brittle behavior and can fail catastrophically with little to no warning, as happened here on the Wootton Bridge collapse in 1861, where a train had gone across it to deliver materials, and on the way back across it with an empty train, it collapsed under the weight of the engine. And so to understand how we can influence metals' behaviors, we need to go all the way down to how metals are formed. And with metals, it gets all the way down to the atomic level. So the atoms in a metal are arranged in a really well-ordered crystal lattice. Now I'm showing you here the most well-ordered that you could get. Everything is lined up perfectly in a bunch of cubes, if you will. And the atoms are the black circles in the corners. To look at that a slightly different way, we could see again our crystal lattice, and that's the thinner lines, the blue lines that are forming the series of cubes all stacked together. One cube is considered a unit cell on this particular diagram. And in this case, though, we'd actually see the atoms to true size for the size of the crystal lattice. And the atoms don't just reside smallly in the corner, they're actually going to touch. They're going to be as large as they can and touch or pack in as close as they can. But what's interesting in this particular configuration, which makes the unit cell look like a cube, those atoms are configured in the loosest possible configuration where they're still touching. All the rows, all the columns, all the layers are all perfectly aligned, and so you have very large void spaces in between. In real life, the different rows could be staggered so that one row nests inside the other row, and the layers could be staggered again so your atoms nest in between in the little openings, as if you were trying to stack balls. You wouldn't stack them on top of each other, you'd stack them in the little pockets in between. And so we might have a cubic unit cell, but we could have other shapes as well. And this particular super open, if you will, least dense possible packing configuration does not occur in nature. In nature, amongst all types of cells that form crystal lattices, there are 14 different crystal structures that could form. We only care about 3 of them, and these are the most common in metals. So just to introduce them, and we'll focus on these in detail in Module 5 and Chapter 2 of your book, are body-centered cubic, face-centered cubic, and then hexagonal close pack. So it is not a cubic configuration, but a hexagonal configuration. And the key thing to look at in these 3 images are the fact that the atoms, or balls, if you will, because it's easier to look at them like that, or marbles, they're not all aligned perfectly on top of each other. And in fact, the face-centered cubic really shows off how we can stagger the rows and the columns so that they nest a little bit closer. It's another way to look at these is we can sort of cut them apart. And so this is an image right out of your textbook. If we look at the upper image, that's for a face-centered cubic. So we've taken out one unit cell, one stack of marbles, and then we've used a blade to cut away so we just see the cube. And so what we can see is that each corner of the cube has an atom, but of course, because you have them repeating, that atom is shared between all of the neighboring atoms. So you really only have 1/8 of the atom in the corner. And then in the face-centered cubic, because of the staggered rows and columns, you actually end up with a half of an atom owned by that unit cell on every single face. So an atom is shared between two touching atoms at all 6 face surfaces. With the body-centered cubic, we again have atoms on all 8 corners of the cube, and then there is a unique atom just unique to that cubic unit cell that lives in the middle of the unit cell. And then finally, the hexagonal close pack, where we actually would see that you have a hexagonal pattern repeating, and so on the top and bottom, instead of a cube, it's a hexagon shape with an atom in each intersection of the hexagon, so 6 on the top, 6 on the bottom. Of course, those are all shared with neighboring unit cells, so you'd only have a 1/6 of the atom for your particular unit cell. There's also an atom on the top and bottom face, so that'd be shared with the adjacent faces. But then there are 3 atoms together inside the unit cell in the middle that are unique. And the whole atom, all 3 of them, belong to the hexagonal close pack. Now, both face-centered cubic and hexagonal close pack are configured in the densest configuration possible for a unit cell and take up 0.74 or 74% of the volume available. Now, if we go back to the crystal structure that we started with, again, a most basic, but you wouldn't see everything perfectly aligned like this in nature, but it is the easiest way to just visualize the big picture of what's happening if you talk about a 3-dimensional lattice. And one of the key things that's important to note is because of metals coming from a molten state and cooling, right, to then form their crystal lattices, during the cooling time, if you put molten metal inside of some sort of mold to create a shape, the molten metal will not stay the same temperature everywhere. That metal closer to air will be cooler than the molten metal in the middle, and so it's going to cool at different rates, and that change in cooling can cause flaws in the final lattice. So here's a nice, neat lattice, but it's missing an entire line of atoms in the bottom half. So this is called a line defect. So we can see in the upper half, the lines of atoms are going to be compressed. They're being squished to try to fit in the same space, and they don't quite even make it. And then the lines in the bottom half are being pulled outward to try to align with the upper halves. And so that is actually going to cause shearing stress and some strains along the dashed line between the compressed and the tensile lines. And it is that behavior that actually leads to plastic deformation in metals, which is the coolest thing. So as additional load is applied and shear stresses occur from the loading, it exacerbates the problem, and you literally will just tear apart along the dashed line. And the different lines that aren't connected are looking for someone to align with, and so as we move from left to right, the line that's missing a lower neighbor, a lower unit cell, will try to connect and try to connect. And this will just keep sliding and keep sliding and keep sliding until there's nothing left to connect to, because you've hit some sort of additional flaw that stops the slip from going on, that stops you from having something to connect to. And in fact, if we looked at a standard stress strain diagram, that point where we rip apart, that's the yield. That's yield point. And then the point where we're just slipping without having to add any additional load and we're just cruising along that slip plane, that's that perfectly plastic behavior that we see in mild steels. But then when we hit another flaw in the lattice that causes us to stop slipping perfectly and requires more load to keep on deforming, that's strain hardening. We need more load to deform. So all of this cool shape on the stress strain diagram is literally from the shape and flaws in the lattice structure. So what are some of those defects? Well, there's really 2 that are the key ones. We have our point defects, and so the point defects can be A, an atom is missing. An atom didn't form, and so it changes the shape of our lattice. It causes some compression, and it's just hard for the line to keep slipping, or again, there's nothing to bond to because there's an actual hole missing atom in the mix. Or B, this is called an interstitial atom. So either an atom from your material or another material got mixed in. Say you have iron and magnesium, and so you have a magnesium atom that's just floating around and it's just not attached to the lattice, it's in the lattice, but it causes mayhem, changes the lattice, you have compression and tension and squishes things together, and the slip can't continue. C and D are both what are considered interstitial atoms. So again, a different material, so maybe a smaller or a larger size atom, joins in to your actual lattice and starts to become a cell, an atom inside one of your unit cells, but it again changes the form of the lattice, and that can inhibit the slip. But you can do really cool things with interstitial atoms like C and D. Let's look at copper. So if you had molten copper and you added a little bit of zinc to the mix, you're going to make brass. Or if instead you added tin, you'd get bronze. If you added beryllium, you get a very boring named beryllium copper, but beryllium copper has all the cool properties of copper. It doesn't spark, it's not magnetic, but it has 3 times the yield strength of plain copper. I mean, come on now. All right, now the other defects, because it's not just point defects that can stop our plastic behavior and lead to strain hardening, the other main one is going to be grain boundaries. So when that molten steel is cooling, or molten metal, period, is cooling, it's going to be in a mold, and some of it will obviously be closer to air, some of it will be in the center where it might retain the heat a little bit longer, and it's going to cool at different rates, and so grains will start developing, and lattices will start developing independently of each other. But as they start to grow and expand, they're going to run into other lattices, and they're not all going to be perfectly aligned. And so you're going to end up with these heavy boundaries. And when a slip tries to run along one of the lines of the lattice, and then it suddenly hits a boundary where it's off angle from the other lattice and it can't continue. If you're having trouble visualizing how the lattices could be forming at different angles or cooling at different times, if you've ever made ice cubes in an ice cube tray, or you've ever tried to make popsicles in an ice cube tray, and you've taken them out too early, and some of it's frozen and some of it's not, well, it's that same idea. This is cooling, and some of it's solidified and some of it hasn't, and it doesn't always line up perfectly. And so that's your brief introduction into the behavior of metals. By the time we're done with modules and chapters 2 and 3 of the textbook, you should have a much deeper understanding of metals. So welcome to metal behavior in materials.